All right, good morning. Um, so you all have received Project 3. Also, just a quick administrative announcement. Homework 8 has been posted. It was posted last night. It is due a week from today. As you know, it is not required. If you do it, then basically your two lowest, well, regardless, your two lowest homeworks will be dropped. If you do homework 8, then you have a chance of having a homework other than homework 8 be dropped. And if you don't do homework 8, then obviously that will be one that is dropped as well. Did you have a question?
When do we get the rest of our homework?
So Professor Broderson has a big stack of the homeworks. He will be handing back homework 5. Homework 6 is still being graded. I should have him back on Monday. So presumably Professor Broderson will be able to hand those back on Wednesday. I do not know when homework 7 will be graded. Presumably sometime next week. Okay? You know, the grader is suffering from the same end of semester crunch that all of you are. So a little patience might be necessary. Okay. So I wanted to talk about the project, obviously, among a couple other things. So let's just dive right in. So all of you should have seen the project handout, the main project handout. That's this. As well, I guess Tuesday or Wednesday, a supplemental handout was posted to the web along with all the test benches that are necessary. So I'm going to talk about the circuit as well as the test benches. So the circuit that you're designing an amplifier yet again. Can we rotate the overhead camera so it's not skewed? Thank you. So this is the basic amplifier that you're designing. You're designing an amplifier to drive, that's going to be driven in resistive feedback. This is a gain of 2 topology. And what you're measured on is how quickly you're able to settle to within a given error precision. Okay? And so I just want to show you real quickly how we actually go about calculating that. So you need to settle to within 0.02% error at the output, which corresponds to 60 microvolts. Okay? And you'll see this in the test bench, sort of what we did in order to measure the error. So this is in test bench 1. And you don't necessarily need to copy this down, but it might be instructive. Okay. So let's get all this on one page. So here you see the circuit. And then basically what we did was we added some auxiliary test circuitry on this side of the line in test bench 1 in order to calculate the error. So let's go through what happens. So if this is V out, here is also V out. And this buffer here is just to isolate what follows the buffer from your main circuitry so it doesn't load it down. So I've got this big, really big resistor. I think it's on the order of a gigaohm, and a really big capacitor that's on the order of a farad. And so what we do here, what this voltage is during the entire transient, is VO init. Now, ideally, when this is 0 volts, it starts at 0 volts. So the waveform looks like this. The input waveform starts at 0 volts, and I believe at 1 nanosecond, although that doesn't really matter. It goes either to plus 0.15 or it goes down to minus 0.15. Now, ideally, at the beginning of the transient, when you input 0 volts, the output will be 0 volts. But as we've learned from all our previous circuits, occasionally you have a little bit of offset, okay? And so we don't want that initial offset to count against your error budget, okay? So what we do is we use this big RC, basically this really low frequency filter, to grab the initial voltage here, okay? Because at startup, it solves the DC analysis. And at the DC analysis, when this is 0 volts, this will exactly equal that, whatever that voltage is. And then as this changes, this filter prevents this from changing, okay? So now what we do is then we add to this voltage, which ends up being stable throughout your transient, some battery voltage, which is either plus or minus 0.3 volts. So what this voltage is V out final under ideal circumstances. It's the initial voltage plus or minus 300 millivolts. Okay? Does that make sense? And then we just put it through a gain of 1 differencing amplifier, which is another ideal circuit. I can use ideal circuits for my circuits. You guys can't for your project. To get the difference voltage, this is the difference voltage, and I believe it's actually called diff, but you can look in your in the SPICE test bench to see exactly what's going on, and then put that through another block that takes the absolute value of it to get the absolute value of your error, okay? And so what we do is we have some measure statements to figure out the time it takes from this point to when V error is less than 60 microvolts. So that's the basic methodology of this test bench. There are a lot of sort of statements in there that are going on. So I just wanted to sort of show you what that test bench was. Okay? Any questions there? Okay. So let's go back to, do people still need to copy this down, or can I move on? All right. Sure.
So what's the purpose of the plus or minus 0.3 volts of the voltage source? I know you explained that.
Wait, this?
Yeah.
Okay, this battery is because what this captures, let's assume that this is nominally 0, it says nominally 0 volts at the input, but let's assume that accidentally that this output, because of just systematic offset, was 1 millivolt. This will always be 1 millivolt right here, right? Now over the transient, this guy will nominally go to either plus 301 millivolts or minus 299. So depending on which simulation we're testing for, because we test with both an input positive step and an input negative step, we need to either add or subtract 300 millivolts in order to get the error from the final out, to the final output. So this is the ideal step. Okay? All right, so let's go back to this, to the project handout. I just wanted to go over, you've all had time to read it, I wanted to go over a few salient points, things that are different here. First off, and I highlighted this, can you all see the text here, or do you have the handout to follow along with? All right, I assume that means you're all fine. So you must, speak up if you're not, if you need it zoomed in. So you have to meet the specs over process corners, over slow, typical, and fast. Now, what we've done before in the previous projects is provided you a single device model, okay? In reality, devices aren't constant from process to process to process to process. There's some natural variation. So now, in the real world, you need to design around that. So now we provide you 3 device models, a slow, a typical, and a fast, and your circuit needs to meet the specifications over all of them, and your FOM is measured as the worst of the 3. Now, seeing that the FOM is speed related, you can all sort of guess that most likely a well-designed circuit, the worst case settling will be for the slow corner. You might run into other problems, like in the fast corner or the other corner, but that means there's something else going on. So in reality, chances are the slow corner is what will slow you, is what will give you the slowest circuit. Okay? So you can use a small input offset voltage, although, because of the way we measure the error in that test bench I showed you before, it doesn't really matter if your output is off by a few millivolts. That's okay. Okay? Another note is you're only allowed to use one resistor. Okay? And we suggest that you use that for your biasing network. And because we've got this slow, typical, and fast corner, another thing to keep in mind is that your bias currents are going to change, because depending on how you set up your master bias circuit, if you were to just set it up with back-to-back diodes, as the VTs of those diodes change, as I discussed several weeks ago, the current through them will change. So you probably want to use a resistor-based bias network and try to come up with a circuit that is relatively robust to this process corner change. Okay? Some other specs. As you all know, we measure the settling accuracy to 0.02%. So this specification sort of meets two purposes. One, as I'll discuss later, this has direct implications in your gain settling. Excuse me. It has direct implications towards what DC gain your circuit needs to have, and I'll discuss that a little later. In addition, this settling accuracy also takes into account how the FOM for the circuit, which is how fast your circuit is, because you need to settle to this accuracy. So that's used in the FOM calculation as well. Okay? The maximum supply current that's allowed is 1 milliamp, and that's measured from the positive supply. Okay? That's about it on the project. The other handout, a lot of this stuff will look very similar. It gives you some guidelines as what to discuss. As I mentioned before, current consumption is measured from the positive supply. Here it becomes critically important, and this has been an issue that we've noticed a couple of times in earlier projects, where you mislabel the polarity of your inputs, in that the positive terminal ends up, what you call the positive terminal ends up being the negative terminal, and vice versa. Your circuit simply won't work if you make that mistake again, because now we're putting feedback around the circuit, and if you swap those two things, you've got positive feedback. It'll take you forever to well, it's another thing that you'll have to debug. You'll think, oh my God, my circuit just doesn't work. It latches to rail. Look at your circuit topology to figure out to make sure that you've labeled your terminals correctly. Okay, and so we've got 4 test benches. I discussed them all here. Test bench 1 I went over. Whoops. It sweeps over the 3 process corners and the input voltage step polarity. It measures the current consumption, the final settling error, and the settling time. Okay. What's very important is that the way we measure the settling time is kind of a bit of a hack. So if your circuit were to, say, oscillate, you'd still get a number reported for your settling time, but your settling error would be out of spec. Okay, so make sure that your settling error is within spec before you hand in your circuit. Otherwise, you'll get basically 0 points for that entire specification. You have a broken amplifier. Test bench 2 is a closed loop frequency response. So nominally, what we expect it to look like is something like this. Thanks. We expect it to look something like this, where this is gain of 2, right? Because the circuit is in a gain of 2 topology at some, omega u, and there'll probably be other poles out here. That's just for your own debugging purposes. If you have poor phase margin performance, then what you'll probably see is some peaking near the corner frequency. And if you see a lot of peaking near the corner frequency, that means your circuit is unstable, and test bench 1 won't work. Okay, so that's test bench 2. Test bench 3 is the open loop differential mode frequency response, and that's really useful for looking at your stability. So what you'll get at the output is, some A0, and then you'll get a pole, and then you'll get some other poles out here, and you'll also look at your phase response. And you'll have stuff like this. So you need to this test bench actually reports to you what your phase margin is. So use this actually before you use test bench 1 to make sure that your circuit is at least nominally stable over process corners. Okay, and the one thing to keep in mind is that actually what this test bench looks like is it's the open loop amplifier with the loading and the output. So this is 1K and this is 500 ohms. The output that's actually measured is the output after feedback. So what you're actually measuring here is A times F, because the important thing is that A times F, that transfer function has phase margin. Okay? So it's a little easier because F is only 1/3. Things are a little easier. If we put this in a unity gain feedback, your circuit would be faster, right? Because higher levels of feedback means higher loop gain, means it pushes your pole out further. But you would have, for the same amplifier, you would have less stability. Okay? Yes?
Why is F 1/3?
So, okay, well, let me redraw this circuit. So here's your amp. This is 500 ohms. This is 1 kilo ohm. Okay. So we look at this amplifier, and this is sort of where the whole analysis of shunt, series, shunt, series, and all that other stuff kind of has a weak point, because we look at this and we recognize this is actually this is shunt feedback. This is shunt feedback. It's current in, voltage out. Current at the feedback point, and it senses voltage. So that being the case, the feedback factor actually, if you want to analyze it this way, the feedback factor is actually that feedback resistance, right? So the feedback factor is R. But when you analyze the loop gain, it doesn't really matter where you put that input voltage stimulus, okay? Because that input voltage stimulus, I mean, this circuit for analyzing the loop gain really is no different than that circuit, right? Because when you analyze the loop gain, the input stimulus isn't part of that calculation. So what's actually easier is to treat this circuit as now this is a series shunt, right? Series shunt, which is voltage, 1K ohm, 500. Okay. And then clearly here the feedback factor is 1/3, right? So really what's really useful for analyzing the loop when you're trying to analyze the loop gain is to figure out a way to break the loop. Okay? And did Professor Broderson talk about sort of the breaking the loop return ratio method in lecture at all? Okay. So if you were to break the loop here and forget about, I'm still dealing with the same basic circuit because we don't have an input stimulus. Then you can clearly identify A as the amplifier gain, and then which is a voltage gain, so that's unitless, and therefore F, because AF has to be unitless, the loop gain has to be unitless, then F has to be unitless, and you can clearly identify the feedback factor as 1/3. Okay, so I realize that I'm kind of mixing my methods here, and that might be causing more confusion than it's solving. But once you sort of get your mind around that, using this break the loop method and not worrying about shunt series shunt and just worrying about loop gain ends up being very useful. Okay? So that's why I said feedback factor. That's why in this treatment here for test bench 3, I use this feedback factor of 1/3. Now, strictly speaking, there's actually a bit of a mathematical error in this test bench, and what it really should be is that we know that the resistance, that feedback resistance, presents a 1K ohm load because it's attached to a low impedance node, so it's treated as a ground. And then what I should do is put it through a 1/3 divider. So I should probably change that, or you can change that yourself in test bench 3. Do you see the subtle difference here? That what test bench 3 actually does, minus plus 1K, 500 ohms, and this is the output, which is equivalent to a 1.5K ohm load followed by a gain of 1/3, right? Same thing. What it really should be is a 1K ohm load followed by a gain of 1/3. Now, seeing that I spotted that bug, none of you get extra credit. But moving along. In reality, you will have to make your own test benches in the real world. This is a luxury. So make yourself comfortable with the notion of working with test benches and figuring out what the right test bench was. I made that late at night, so I realize now that I made a slight error. So then test bench 4 is basically the same as test bench 3, but the input stimuli is a common mode value. So is a common mode stimuli. So that's just used to measure the DC common mode gain. Pretty straightforward. All right. So now let's work on, boy, I have a lot of material to get through. Let's work on how this settling error in this spec translates to the speed of your circuit and the gain of your circuit. Okay? So what we have, and I hope all of you are familiar with S-domain transfer functions. Hopefully all of you should have had 120 or its equivalent. So Laplace transfers going back and forth. I'm only going to do a couple of very simple Laplace transfers. If you're not familiar with it, I'm sorry. Has anyone not had 120? Are you not? How many people have no idea what I'm talking about when I say an S-domain transfer function or a Laplace transfer function? A few. Okay. Ask your classmates because this is really useful. And I don't have the time to go into it. And it's basically you're all familiar with Fourier domain transfer functions, right? S-domain transfer functions, Laplace transfer functions are just an extension of that. So treat S as j omega and you're good to go. Okay? So, give me a second. So, first off, what we know, so okay, so this is a standard amplifier put in feedback. And what we're going to do is figure out the transfer function of it, assuming that A of S is dominated by a single pole response. Okay, so A of S equals A0, the DC gain, over 1 plus S over omega P. Okay, now, again, this looks just like the Fourier transform of a single pole response, except S is replaced by j omega. So for those of you not familiar with S-domain transfer functions, just think j omega. We do all the math, and we've done this a whole bunch of times before, and we get V out over Vi as a function of S. So let's call this big A of S is equal to 1 over F times A0F over 1 plus A0F times, let me make sure I want to get this right. I don't have it in my notes, so I'll just have to make sure I get it right. 1 over 1 plus S omega p times 1 plus. Okay? So basically, as we recall from previous discussions, the gain here is basically reduced by a factor of 1 plus the loop gain, right? And the pole is pushed out by a factor of 1 plus the loop gain. Okay? So A of S is equal to 1 over F times T naught over 1 plus T times 1 over 1 plus S omega p prime, where omega p prime is equal to the original pole times 1 plus A0F. Okay? So that's a transfer function of this amplifier and feedback. Okay? Now this A of S, we're going to now plug into this a closed loop system, stimulate it, and see what the error voltage is as a function of in the S domain. So we can see how the behavior of this transfer function relates to the settling error. Okay? So moving to the next page, are we good to move on? All right. So now what we're doing is we're putting in some input voltage into this macro modeled op amp, which is now big A of S, which has feedback in it, getting V out in the S domain. Now what we know, what's the ideal output voltage? The ideal output voltage is basically the input voltage multiplied by the closed loop gain of this amplifier, which is 1 over the feedback factor. So our ideal amp is just applies 1 over F, okay? And this is V out ideal. We take a difference of the two to get the error, okay? And what we know is that V out of S from before is 1 over F T0 over 1 plus T0 times 1 over 1 plus S omega P prime times VI of S. Okay? And V out ideal of S is equal to 1 over F times VI of S. Okay? V error is the difference between these two. So this implies V error equals VO ideal minus VO is equal to, and I'm going to just do some factoring real quick, VI of S over F 1 minus T0 over 1 plus T0 times 1 over 1 plus S over omega P prime. Okay? So now, and here's where, if you don't know Laplace transforms, I'm just going to move this up here and do that. So that equation is still there, but I can continue writing. So now what I'm telling you is that the input voltage, Vi of t, is equal to U of t, the step function. So at time equals 0, it jumps to 1. Okay? And what I'm telling you, for those of you who don't know, is that if vi of t is defined as a step function, this implies the Laplace transform of that into the S domain is just equal to 1 over S. Okay? If you don't know that, don't worry about it. So now we plug that into this error voltage. So therefore, vi of S is equal to 1 over F times 1 over S times 1 minus T0 over 1 plus T0 over 1 plus S over omega prime, omega p prime.
That's V error.
Yes, thank you. V error. So now I'm going to step ahead a bunch in the math, the intermediate algebraic steps. V error of S is equal to 1 over F times 1 over 1 plus T0 times 1 over S plus T0 over 1 plus T0 times 1 over S plus omega p prime. From there to there is a lot of tedious algebra that I'm skipping over. You can do it. There's no, I mean, it's just algebra. There's no Laplace trickiness here. Okay? So now what we need to do is go now from the S domain back to the T domain using Laplace, the inverse Laplace transform. And again, if you don't know the Laplace transform, I told you already that 1 over S corresponds to U of t. So we know how to transform this portion back. And this, 1 over S plus omega p, corresponds to the exponential of minus t times omega p. So these correspond to one another. So now we just use the Laplace transform and we get V error of t is equal to 1 over F times 1 over 1 plus t0 times u of t, which is a step function, plus t over 0 plus 1 over t, 1 plus t0, t0 plus 1 over t0, exponential minus t times omega p times u of t. And actually, I forgot to put a u of t up there. Okay? This is a very important expression. Okay? Because this tells you the exact formula for your error voltage as a function of time in terms of time and loop gain, and that should be omega p prime and omega p prime. Your DC loop gain and your omega p prime, that gives you the complete expression for what your error looks like as a function of time, assuming a single pole system with no nonlinearities. Okay, so there's some limitations here, and we'll get into that in a second. So let me move this up here. Slide. Can you move the camera up just a touch so that we can get that last? Cameraman? Can you move the camera up a bit? Thank you. That's good. Down a bit. It's just the boxed equation. Okay. So the normalized V error which is basically V error over V out ideal, or V error. Oh, that's the other thing I forgot to put in here. Let me go back to this for a second. There's a VI, oh, V error of t. No, that's right. This is assuming a unit step input. Okay? So basically, the normalized error is V error over V out ideal. So if the unit input is the input step, then the output. If input is a unit step, then the output is a unit step times f. So it's basically that v air of t divided by 1 over f. So it's equal to basically the stuff inside the brackets here. You just remove that 1 over f. So that's the normalized V air, and that's the expression that has to get down to 0.02%. Okay? So let's think about what the implications of this is. All right? So what is V air as for t equals 0? So using this expression, it's equal to 1 over f times 1 plus t0 plus t0 over 1 plus t0 exponential of 0. So that's 1. So you condense everything, and you get 1 over f, which means that basically at time equals 0, the air voltage is the entire output, because this is equal to VO ideal. This should be pretty trivial. I see a lot of confused faces, so I'll try this again. What we expect, the transient's going to look something like this. If that's the input step or the ideal output, nothing can change instantaneously, so it's going to look something like that. At time equals 0, the error is the entire output voltage. No big surprises there. And this voltage here, if this is V out, is 1 over f. So that's why at time equals 0, the error voltage is the entire output voltage. Nothing interesting there. Now let's look at V error for t goes to infinity. It's equal to 1 over f times 1 over 1 plus t0 plus t0 over 1 plus t0 exponential of minus infinity. That goes to 0. So it equals 1 over f times 1 over 1 plus t0. So that means that the gain, therefore the gain of, or the normalized V error is equal to 1 over 1 plus t0. Okay? Therefore, this tells you, if you had infinite amount of time to settle, this tells you what your DC gain spec is, because this has to be less than 0.02%. You know what the feedback, and T0 is AF. You know that F is basically 1/3. Now you can calculate what your A has to be. Okay? So with these two expressions for the error voltage at time equals 0 and the error voltage at time equals infinity, we can start plotting some rough sketches as to what V error over time looks like. So we know that at time equals 0, the error voltage, this is V error as a function of time. We know that it's equal to 1 over f, or the entire output voltage. And we know that it goes to 1 over f times t0 over 1 plus t0 plus 1 as time goes to infinity. Okay? And we also know from this expression that basically that decay is exponential with a time constant of 1 over omega p prime. Okay? So we know that the settling is going to look like that, where this is exp goes as exp of minus omega p prime times t. Okay? And what frequently is done, what people talk about is number of tau, or what is the tau of this one-pole roll-off. And tau is just defined as 1 over omega p prime, or the omega p prime in here. So you could also express it as the exponential of minus t over tau. So a lot of times people will say, the tau of my circuit is 100 picoseconds. And what that means is that in 100 picoseconds, the error shrinks by a factor of e, right? So each time that t increases by another 100 picoseconds, the error decreases by a factor of e. Okay? And similarly, you can plot the normalized V error. And so for there, it's 1 or 100%. And it goes down to 1 over 1 plus t0. And these two curves are the same. It's just that the normalized error is scaled by the gain of your circuit. Okay? Now, we know from before that the normalized V error is 1 over 1 plus, the normalized DC error for after infinite time is 1 over 1 plus t0. But we don't want to set our loop gain to be, or 1 plus, if we set 1 over 1 plus t0 to be equal to 0.02%, what that means is no matter how fast your circuit is, if your circuit is infinitely fast, it will still take an infinite amount of time for your amplifier to settle to exactly this precision. So therefore, that's why I said up here that your 1 over 1 plus loop gain has to be smaller than this value. In other words, your DC loop gain needs to be bigger in order, because settling error accounts for both DC static error as well as the transient behavior. So if you use up your entire error budget with the DC settling error, then no matter how fast your transient behavior is, you'll never actually meet the settling spec. Okay? And I have some plots here to sort of show that behavior. And so what I've done here is I use MATLAB. First, what I've done is settling error, the normalized settling error versus time with infinite DC gain. So therefore, your loop gain is infinite. And basically, I've swept the tau for 1, 2, and 3 seconds. This is tau equals 1, tau equals 2, and tau equals 3. Okay? And what you can see is that for slower tau, basically the exponential curve of decay is slower. And I've plotted the same plot on a semi-log scale where time is in linear axis. The error is on a log axis. And you can see it just affects the slope, as you expect, because each of these things is just exp of minus t over tau. Okay? And so what you can say is, if I need a certain precision of settling, if you were to say to me, I need 1% settling, I could tell you exactly how many tau of settling you need. I don't know what your tau value is. Your tau might be 100 picoseconds, it might be a second. But if you say you need 1% accuracy in your settling, I can tell you what your tau is. Does that make sense to everybody? Okay, good. So what I've also shown here on this plot is, and I know you can't see it necessarily very well, is the settling error versus time for different loop gains. There are 3 plots here, and for all of them, tau equals 1. Okay? And when you zoom out and look at the macro, like sort of the macro level behavior, all 3 curves look exactly coincident. Okay? But if you look at if you look at this behavior, and let's assume that your settling spec was to this here is 0.02%. So now if your loop gain is 5,000, which is 1 over 0.02%, that corresponds to this. You can see, although it might not show up very well, that that curve asymptotically approaches 0.02%, but never actually hits it. If you increase your loop gain by as little as 10%, then it crosses over the spec. It crosses over that specification mark right there. If your loop gain is twice as fast, you can see that even twice as high, even though your unity gain frequency or your settling response, the speed of your circuits are nominally the same, because you have higher loop gain, it crosses over that threshold sooner because it's settling to a lower value. Okay? So you want to include some amount of extra gain in your loop gain for extra margin beyond the settling error. You do not want your loop gain to be exactly 5,000 because then it will never settle. You don't want it to be just a little bit above 5,000 because then you'll have a big penalty because you'll be on the slow part of the settling tail. So you want to increase the gain some amount, and that's for you to decide if you need it to be 10%, a factor of 2, a factor of 3, a factor of 100 in terms of getting your settling behavior to work. Yeah?
I have a question about the hand-drawn plot before the MATLAB plots.
The hand-drawn plot before the MATLAB plots.
I think it's under.
Okay.
Yeah, the scaling. What's the difference between the two plots?
This is normal. This is the normalized V error. So it's basically normal. Like I'm normalizing it. All I'm doing is dividing by 1 plus the feedback factor, because the gain of the circuit is 1 over the feedback factor, and I'm putting in a unit step. So the output step, instead of being a 1 unit step, is a 1 over f unit step. So just to get rid of that. So it's pretty trivial there. Okay. All right. Let me see. So that's if your circuit is dominated by gain and a single pole, then the analysis of the behavior is complete. What I haven't done, however, is go over some other effects that might limit your performance. They include things like you don't have one pole. You have additional poles in your transfer function, which degrade the phase stability, the phase margin of your circuit, and results in ringing and a slower settling. The mathematics there become very complicated. The thing to keep in mind is that if your phase margin is above like 60 or 70 degrees, then by and large you can treat your circuit as a single pole roll-off. Okay? So shooting for a higher phase margin simplifies the analysis and also limits the amount of ringing that you have. Okay? But in order to get that high phase margin, you might have to it might require sacrificing some other measures of the circuit. So I'm not saying that that is the exact way to go. Okay? That's one thing. The other thing is slew rate, right? I assume that no matter what, the slew rate, the settling response of my circuit was purely determined by the linear response in the Laplace S domain. Okay? But if you have slew rate limitations, which are effectively a nonlinear effect, then that analysis is no longer completely valid. And you have to account for the fact that the circuit can't, the output voltage can't change fast enough at a high enough slope if you have slew rate limitations. So those are the other limitations of your circuit that you'll have to keep in mind. And I guess at next week's section I can talk about that a little bit more. All right? Any questions? Also, I'll make sure Saurabh covers it on Tuesday. There's a lot of material to cover, and we're trying to get through everything we can for you guys on the project. Yes?
So when you feed in the pulse, right, the positive,
Uh-huh.
do you expect the output to also track it to be positive, or do you expect it to be inverted?
Well, yeah, it's an inverting gate. This gate amplifier is an inverting gate amplifier. So in reality, yes, there's that inversion. I ignored that in the analysis, but you know, it's all basically the same.
Your offset voltage times the positive terminal testing, take the optimal value for that, or put ourselves in say, or do we have to add it in ourselves?
Oh, that's not actually in the test bench? I think it's not. Send me an email and I'll correct it. I'm going to be out of town this weekend. Thanks for picking that up. You really shouldn't need it, because also that offset voltage, the gain from that terminal to the output is only 3, right? So you're only allowed a millivolt. So all you can do is change the output by 3 millivolts. That doesn't really help things very much. Yeah, here. Oh. Well, you control it by making sure you don't have non-dominant poles too close to your unity gain frequency. Okay. So it's a different at the unity, like if your loop has 360 degrees of phase total and gain higher than 1, that's a positive feedback circuit, right? Okay. In reality, and we're doing negative feedback circuits, so we intentionally have a sign inversion which causes 180 degrees of phase shift. Therefore, in order not to get back to that 360 degree phase, you need to make sure that there isn't an additional 180 degrees of phase introduced by your circuit. Why don't you come over here? I'm in the middle of a question. Okay. So you need to make sure that you don't introduce another 180 degrees of phase. The single pole that you have, you're always going to have a pole that introduces 90 degrees. Okay? That a pole, because the pole's at a low frequency, so at high frequency, that'll introduce another 90 degrees of phase. Okay? So you've got another 90